Swayam Prabha. Digital India. Educated India.
Welcome to the Advanced Digital Image Processing and Computer Vision. Today, we will start our discussion on a new topic, that is on stereogeometry. In the last lecture, we discussed the camera geometry of a single view. In stereogeometry, we take images by two cameras of the same scene. So, let us consider this kind of stereo setup. As we have considered the representation of a camera for the mathematical mapping of a three-dimensional point on a two-dimensional plane, is that you require the camera center and again you require an image plane. This defines itself the projection that would take place on the plane from a 3D point X. So, if I consider a ray passing through the camera center, passing through the image plane here, or rather ray connecting to camera center, and then that ray where it intersects the image plane, that is the image point of the scene point X. So, I am denoting it by the lowercase alphabet X to denote the image point, and the uppercase alphabet to denote the scene point. Similarly, their coordinates are also represented, as we discussed earlier. They are represented in a homogeneous coordinate system. So, which means there is an additional dimension denoting the scale of the coordinate representation. So, when I will be representing once again the coordinates, I will represent simple x, y, z for a point in a three-dimensional space, and x, y coordinate for a point in a 2D image plane. And in homogeneous coordinate system, we know that this will be represented like for the three-dimensional point. So, x, I am considering it's a column vector which is representing this point x. This is the coordinate at that position, 3D coordinates, and then this is the additional dimension expressing the scale. Similarly, for the second camera, which is placed at a center C prime, and again there is an image plane, another image plane of this camera, and it defines its own mapping of that same scene point. So, in this case, the mapping is mapped at a point x prime, which I am denoting it. Now, this is what is a stereo setup. So, in a stereo setup, it is sufficient to denote these two cameras, and then what you obtain two images of the same scene, and we understand there are corresponding points in these two images, which are the image of the same scene point. So, here x and x prime, they are the corresponding points. So, let us try to understand further the kind of configurations that we are considering here. So, the line that is connecting the camera centers, this line is called baseline of the stereo setup, and you can see that this line intersects the image plane in both the image planes, say this camera. So, just for convenience, let me denote this camera as left camera. So, this camera center, for the left camera center, this image plane is for left camera image plane. Sometimes we call it also left image plane of a stereo setup, and the other one is the right camera, and this is the right camera center, and this is a right image plane. Now, this left and right, they are expressed in terms of the viewer's understanding of this diagram. As you understand, they do not bear any special meaning, otherwise they are unbiased. You can consider any camera as a reference camera. So, in a stereo setup, you will see that one of the camera is considered reference camera for expressing the coordinate convention. So, we will be discussing that part just very soon. So, what I was discussing, that this baseline intersects image plane at this point, say left image plane, and say we denote this point as E, and similarly it intersects the right image plane, and we denote this point as E prime. Now they are called epipoles. These 2 points are special, had special significance of the stereo setup. They have special geometric significance, so we'll discuss. But as you can see that in a stereo setup, these 2 points are also fixed. Once you define the stereo setup in terms of cameras, center and planes, naturally the line connecting those 2 centers are also defined. Since those 2 planes are defined, their intersection points are defined. So these epipoles, they are called epipoles, they are also defined. And you can see that actually there is a plane connecting X, C and C prime, and this plane intersects the image plane in these 2 lines. So for the left image plane, it is intersecting a line here, and this is also a line here. Now it is dependent on this plane, and this plane is defined by the scene point, because C and C prime is already fixed. So the third point for requiring to define a plane is just the scene point. So scene point, every scene point defines a plane in a stereo setup. We call that plane as epipolar plane. So this is, I've said epipoles, and these 2 lines we call epipolar lines, and this plane is called epipolar plane. So epipolar plane is defined by the scene point and 2 camera centers. And the epipolar lines are the intersection of epipolar plane with the image plane. So you see that there is an intersecting line of this epipolar plane with the image plane. Similarly, this is the intersecting line of the epipolar plane, same epipolar plane with the other image plane, and they are called epipolar lines. So just I mentioned earlier, the corresponding point of X is in the right images lies on epipolar. So you can observe that actually this epipolar line, since this epipolar plane intersects here, so this is the point where it is intersecting here. Of course, if I extend this plane further, this line would be also intersect. This plane would intersect. That means this line could be extended. But now connecting the point which is connecting to camera center, right camera center, for that ray where it intersects, that point is the image of the same scene. So X and X prime, they are corresponding points, and naturally X prime also lies on the epipolar line of the right image plane. So for X, it is the epipolar line on the other image. Similarly for X prime, this X lies on the epipolar line in the left image. Other thing also it is observed, you can observe that suppose I take any points P in the epipolar plane. Now the image of that point would be again a point which is the point of intersection of the line drawn from the center to this point P. And since this point P is also lying in the epipolar plane and C is also lying in the epipolar plane, so this straight line also lies on that same epipolar plane, which means it will intersect L. So the image of P will also lie in the epipolar line. Any point which is lying in the epipolar plane, for which the image will also lie in the epipolar lines, both in left and right also. So here also you can find that this is lying on the epipolar line. So this would be the corresponding point for this image. Actually, it is difficult to say, because if it is image line, so I can consider, say, this point also, for this point also this. So there are candidates. So I cannot definitely say when the point is lying in plane, I cannot definitely say which point is the corresponding point. All are candidates, so all the epipolar candidates for that line. So there are certain, we can see that there is already you can identify certain ambiguity while defining a corresponding point. But what we know that the corresponding point of an image, of the image point in a plane lies on the epipolar line, corresponding to the epipolar line of the other image, and epipolar line is the line of intersection of the epipolar plane containing that image point. So that is what can be, we can say about this constraint on the stereogeometry. So this epipolar geometry, if we once again summarize, as we can see in this particular diagram, which is taken from this book, Multiple View Geometry in Computer Vision, and here we can see that these are the two image planes, and these are the centers. So these are the image epipoles as we defined, and suppose this is the epipolar plane, because you can see that it contains the two centers, like it contains the baseline. So any plane containing baseline is an epipolar plane, and then the point of intersection, line of intersection of that plane with the image planes, they form the epipolar lines, say L and L prime. So with this, again, the stereogeometric definitions of different entities, geometric entities of stereogeometry, let us summarize their properties. So epipoles, what we denote here as E and E prime, as we have seen here, this epipoles E and E prime. For them, it is the intersection of baseline with image plane. That is the definition I have mentioned also earlier. So this is the baseline. So it is intersecting. So you can see that it is the intersection of baseline with the image plane. You can also say it is a projection of, this is basically camera center. Instead of projection center, it is more suitable if I write camera. It can be called also projection center with respect to perspective projections. But let me just mention, call it camera center in this context, so that it becomes more related to the camera geometry. So we see that if I consider the center of this image of this center in this image plane, what you need to do, you need to draw the line from this center to the camera center of the other image, and wherever there is wherever it intersects, that point is itself the image point of that camera center. That is the definition of image formation. So naturally, so the projection of camera center on the other image plane is also, we can say that is also equivalent to that is epipole. Similarly, projection of this camera center in this plane is also will give you the other epipole. So we can say left epipole is the projection of the camera center of the right camera, and right epipole is the projection of the center of the left camera. So in this way also you can summarize. Then this is another thing from single view geometry. You understand that how the vanishing points of a direction is considered, that when you consider a point at infinity along that direction, then the projection of that point at infinity provides you the vanishing point in the image plane for that direction. So every direction has such a vanishing point. Now epipoles are vanishing points once again in a particular direction, which is basically direction of the baseline. This is the same thing, because it is also projection of the point which is lying at the infinity. If I project this point on this image plane, then that forms this epipole, left epipole, and they project this point on this image plane, it forms the right epipole. So, those are also called vanishing points, respectively vanishing points of that point. And then about the epipolar plane, it is a plane containing the baseline. So that is what we are considering. I mean, actually, it is a kind of cylindrical so if it is, if I consider any plane passing through the baseline, which means baseline act as an axis, and the cylindrical rotation will give you every plane. So with that parameter, you can define the epipolar plane. That's why it's a one-dimensional family. So you can just denote the angle of rotation along the baseline, and with that parameter, every epipolar planes could be identified. And epipolar line is the intersection of epipolar plane with image, and always comes in corresponding pairs. We have seen that, because since it is intersections of the respective plane with two image planes, so there the constraint lies. So those intersecting pairs of intersecting lines on two different image planes, they form a correspondence. The epipolar geometries that I said that it's a family, the epipolar planes are intersection family of planes pi and lines L and L prime, and it is so all these things can be considered, they are lying on the same epipolar plane. That means epipolar lines, epipoles, corresponding image points, camera center, scene point, they lie on the epipolar plane. Now, one interesting thing let us understand at this stage, that when we consider stereo imaging of a plane, we can see that actually that induces a homography among the two image points. That means you consider a point x as before. For this scene point, we know that x and x prime are the two corresponding points. Now, you consider another say image point y lying on the same plane, and say you form their images by taking the respective intersection on the image plane for the projection rays. So, this projection ray and the other projection ray, and so you can see that y and the y prime, they form the corresponding pairs of points. Now, this x, x prime, y prime, like this any other points. If I take any other point, for all the points there will be some corresponding points. Now, the interesting thing is that all of this thing, they form homography. Now, this we already discussed when we discussed about the two-dimensional projective geometry, because you know that the projective transformation, some of the things, those properties are satisfied. The first thing is that, as you can see that since these points are in the two-dimensional image space, so that's an element of a two-dimensional projective space. So, it's a transformation between two-dimensional projective space. Second thing is that you have an one-to-one correspondence, because this x and x prime, they have one-to-one correspondence, because they are defined by the point x. So, there is no other point which will correspond to x. So, even if I extend this ray, so naturally this ray will intersect this plane. So, there could have been some, or rather I would extend this ray. So, if I take any other points, now from that ray there would have been some point, but since I have restricted this configuration, my scene point has to be an image plane. So, there exists an unique point for these two in the scene point. So, that is why their correspondence is also unique. So that means that they are invertible. They have one-to-one mapping. And third thing, as you can understand, that if I have a line here, for example, the line here, so this will be also mapped to a line. Each one will be also mapped to a line. So the collinearity. So all the collinearity. So all these points in between, they will be also projected. So if I take any point here, say Q, so it would be projected to say Q, and there would be Q prime. So which means that there is an homography. There is a homography between these correspondences, and this homography is specific to this plane. So we call this homography as plane induced homography. So this is what we can consider. And since just to summarize, what you can see, first thing, as I mentioned, if I apply the respective homography property, homography transformation, that means this homography, this matrix should be of 3 cross 3 non-singular matrix, and if I multiply x with h, I should get x prime. Similarly, for y, I should get y prime. You should note that these are all not hard equality, because they are up to projective scale, up to the scale value. So that is what is this equality. So just to summarize this particular observation, that if I consider any arbitrary plane except the epipolar plane, I said that for epipolar plane some ambiguity there is there, because if I consider this epipolar plane and as I was reconstructing, so for any point there is a possibility that it could be an image point. So this one-to-one correspondence, that property gets violated. So except the epipolar plane, for any other arbitrary plane, you can consider that there exists a plane of homography. There exists a plane induced homography H. And this homography is a characteristics of it is basically related to that plane. So every plane has its own distinct homography. So this is one thing. The other thing you should note that even this plane, even the plane, if I consider the Hx, first that the Hx also lies. So if I apply the homography, these points will lie in the epipolar line. So that is the definition of the epipolar. Epipolar line has a definition because this point also lie on the epipolar plane. So naturally, this point lies in the epipolar line. So if I perform, so to search for correspondence, I need not search for every. So for example, this y, if I consider the respective epipolar line for y, so we know that this will lie in this epipolar line. So this is another consideration. The third is that since epipoles are also corresponding points for a point in the plane. So this is another thing, because if I extend this point toward this line towards infinity, it will intersect. This line will intersect at some point at the infinity, and these points E and E prime, they also form a point of correspondence. So from there also you can say that E prime is He and L prime is H minus transpose L. So let us further discuss about this epipolar geometry. Now we will be using the respective camera parameters and establish the relationships between all these geometric entities what we defined for a epipolar geometry. So here we can see that once again, given any arbitrary plane pi, there is a homography. There is and for this epipolar configuration with the scene point and forming this epipolar line, this is the epipolar line. So this is the epipolar plane and this is the epipolar line of intersection. Similarly, the other epipolar line in the right image. Then there are two epipoles. So these are the configurations. What you are observing, basically you are observing this x and x prime. In the image, suppose you are observing this x and x prime. For some way you get these two corresponding points. We would like to see what are the relationships between x and x prime, and what is given to you is p and p prime. What is p? P is the projection matrix of this camera, so which is given by in this configuration, semi-canonical configuration. You see that this is the canonical configuration and this is the calibration matrix, which is upper triangular matrix, camera calibration matrix. So this is how this projection matrix is given, which means the origin, the center of the camera lies in the origin of the 3D world coordinate system, and this is this defines a camera camera centric coordinate system, because the center is here, origin is here, and you can consider, of course, an arbitrary calibration. In the canonical form, if I make K inverse of the image point, I will get respective canonical image coordinates for that projection. So anyway, it is basically camera centric coordinate system, and this acts as a reference with respect to this axis in the canonical form. There is a rotation and then there is a translation parameter, and this camera also has its own camera calibration matrix. They need not be the same. So this is the projection matrix of the second camera. So what I can say that I can write using this, the relationship between sin point and these two corresponding points. I can write that, say, and I will assume this is lying at the plane at infinity. So in general, I will consider first the plane at infinity. So once again, the epipolar geometry, I am considering a plane which is at infinity. Now this is a direction d, because it's a plane at infinity. As you know that this direction satisfies, this direction d itself denotes the point at infinity along that direction, which can be denoted in the homogeneous coordinate system as d0. And then if I consider the image of that point x, which will be p into x, that is given once again k, I have just taken k inside. So k0 into x, and so since x is d0, so it is basically k into t. Similarly, if I consider x prime, that means this point, so it's an image of the same sin point, and where I will apply the p prime, so this projection matrix, and p prime can be expressed as k prime r and k prime t, which means I will take k inside these expressions, I will simply multiply it. And then if I consider x is d0, so which will give me k prime r d. Now since here you can see that I can write d equals k inverse x. So I can reduce this expression as k prime r k inverse x. So what does it show? That for this point, if I perform this transformation, I will get x prime, which is giving me this homography. So this transformation is nothing but the homography, because this matrix is a 3 cross 3 matrix. You can see k prime is a 3 cross 3 matrix, r is a rotation matrix, 3 cross 3 matrix, k inverse of k, which is also 3 cross 3. So the composite matrix would be 3 cross 3, and that gives me the respective homography. So I will simply write it as k x prime equal to h pi x, where h pi is a homography and it is induced by plane at infinity. So this is actually plane at infinity, and that is the relationship between these 2 points. Now let us consider first let us compute this L prime. So what is L prime? L prime is E prime, line segment between E prime and X prime. That means I can perform it as E prime cross X prime using the same projective geometry. Now this cross product operation is the way we have computed. It is not very convenient when we are performing this kind of matrix algebra. That means if you remember, when we are doing cross product, what we are doing here, let me consider, say, E prime is the vector, 3 vector form. Say it has 3 component Ex, Ey, Ez in the projective space. You note that Ez is the scale, but I am taking in general this component, and say X prime. For X prime also, let us consider it has 3 component, say X, Y, K. I am using K just not to confuse that this is a scale factor, and in the ordinary observation of X prime, which is, let me use the vector notation just to denote that they are vector. Now when I am performing the cross product as we have done earlier, so I will be doing this, I will be computing this determinant and factoring out the coefficients of each unit vector. That is the same unit vector for this. So what I will get here, you can see that for the ith component, I am just writing again in the form of vector equivalent. So E cross E prime cross, say, X prime. So the first one, Ey into Z and minus y into z. So let me write it as, I will write in this form, z into ey minus y into ez. For this one, I have to first perform multiplication of these two, which is x into ez and then multiplication minus z into ex. And for the ith one, for the kth one, I have to compute again multiplication of ex and ey. So y into ex minus x into ey. Okay. So can I express this operation in some matrix form? That means, say there would be some 3 cross 3 matrix which I will denote it like this into x. Oh, I should use, instead of z, I should use k, because this is k. So let me replace all z by k. Okay. So E prime cross xy k, that should be giving this one. So that you can see that if I take E prime cross as this one, this particular form, then if I multiply this with x, y, k, suppose I am multiplying this with x, y, k. So what I am getting? First, you can see that here, yes, so minus ez into y plus k into ey, or this one. So k into ey minus y into ez. This is same. Okay. Then consider the second row and third column once again. So there you are getting x into ez minus k into ex. You can see this is the second one. And for the third row with this one, I will get minus x into ey plus k into, not k, y into ex. This one, y into ex minus x into ey. So the third row. So this matches, which means that this part, this one, I can replace this one by simply this matrix multiplication. So the equivalently, the cross product can be shown as, in this case for a 3 vector, as the matrix multiplication, where the 3 cross 3 matrix is derived from the parameter of E prime. So this is the way this, and you note that this matrix is a skew matrix. This matrix is a skew matrix because diagonal elements are 0 and off diagonal elements they are of opposite signs, magnitude is same and opposite sign. So these are the off diagonal elements, they are of opposite. So we call this matrix is a skew symmetric matrix. So symmetric matrix, they should have been the same. In skew symmetry, the skew symmetry is that they should be of the opposite sign, keeping the magnitude same. So if it is positive, other value would be negative of the same value. Now let me once again proceed further. So this x prime can be written as h pi x because of this homography. Because of this homography, I can write it h pi x. So I can find that L prime and x. So this epipolar line and the image point for which the corresponding point, the line where its corresponding point will lie, they are related. They are related because this quantity is is once again these are all obtained from these configurations, as you can see. So h pi is also k prime r k inverse. They are totally the parameters of the camera. So this is the h pi, and E prime, we will see later on how the E prime is. E prime also can be obtained from here because E prime is the image of this camera center. So what is the center? Center is again it is 0, 0, 0. This is in the in homogeneous coordinate it is 0, 0, 0, 1. So what is E prime? We can write E prime is P prime into the center, P prime into C, which is P prime into, in this configuration, 0, 0, 0, 1, which gives me K prime R, K prime T, 0, 0, 0, 1. Further reduction will give me only K prime T. So the E prime is K prime T, which is again which are parameters of the camera. So the whole thing is a fixed quantity, because it is independent of X and L prime. It is independent of these two quantities. So given X, if I multiply with F, so this 3 cross 3 matrix is denoted by F. That is a standard form. This is denoted by F, and so L prime equals F, and this F is a kind of a property of the stereo geometry. F is independent of your observation points. It is totally formed or totally derived from the parameters of the stereo geometry. That means projection matrices. So your stereo geometry is defined if I give you two projection matrices also. So this is a definition of F, and F has a special name in stereo geometry, which is called fundamental matrix of the stereo geometry, because this characterizes stereo geometry, and the interpretation of F is that for any corresponding point, so you take any other point which may not be lying in this plane, say any scene point y, and then take its image point, say this is y, and then consider the other image point, say y prime, and the line between say E and y prime, naturally that defines the respective say epipolar line. Now this line, okay, so this line can be expressed. So I can write here, for example, Ly, this line, if I write it as Ly line, Ly is Fy, the same way, like L prime is Fx, similarly Ly prime is F into y. For any image point, this is true, and that is the interpretation of F. So we can see that finally the expression of the fundamental matrix in terms of everything given in the image parameter. So this E prime we have derived, this is equal to K prime T. This is what is also E prime. Let us further elaborate this property and find out that what is the characteristic I should say equation in epipolar geometry which relates the corresponding pairs of points. Already we have seen in terms of this relationship, that means if I give you the corresponding point, I get of course the epipolar line on which the corresponding point will lie. But how exactly these 2 points are also related in an expression, that we would like to explore. Now as you know that since x prime lies on L prime, we can write, so first thing once again you note that C is given by this because of the parameter, that means the origin of the world coordinate system lies at the camera center, or it is a camera centric coordinate system. Whereas C prime, this can be shown that this is this can be computed, because if I use these expressions, the C prime, so for C prime what we will do that we will consider the projection matrix this one, and I can write equivalently K prime R and K prime T in that notation. You know that we have used this also M, and this is, say, in that case P4 when we have discussed the single view camera geometry. So what is C prime? C prime can be written as minus M inverse P4, and if I apply this transformation, if I apply this equivalence, so K prime R, M is equal to K prime R, that is a K prime R inverse, and P4 is K prime T. Then I will apply matrix algebra, you know that inversion of this multiplied to multiplication of products of two matrices, no, they just interchange, they just swapped in this fashion. This is K prime, this is T. So this string in that composite matrix multiplication, since associated operation, this is identity matrix. It is the inverse of the same in matrix, and this is square matrix. These are 3 cross 3 matrix. So I can reduce this as minus R inverse T. But what is R inverse? Now inverse of R, we know rotation matrix is orthonormal matrix, and for any orthonormal matrix, inverse of R is given by the also is equal to the transpose of that matrix. So I can write it in this form. So this is the coordinate, I should say C tilde. That means this is the non-homogeneous coordinate, and to make it homogeneous, I will add this additional dimension. So this is how the camera center of the second camera, or in this case say right camera, that is how it is expressed. Now let us express the epipoles once again. So this is epipole. So projection of C prime will give you epipole on this image plane, which means I will multiply projection matrix with C prime. Similarly, projection of this camera center on this image plane will give me the right epipole. So I will multiply C, camera center C, with P prime, and I know their quantities. I know the P and P prime. So from there I can get that epipole E equal to, say, minus KR T, because this is the multiplication. If I multiply this PC prime, it will be K minus KR transpose T. Now since directionality, negative scale is also, it's up to projective scale, I can also write it in this form, KRT T. And if I consider, say, so E prime can be, this is for the epipole, left epipole, and for E prime we have already expressed it, but we can also once again do it. So KI0, so this camera center, this camera center is E prime is the projection of this camera center, and which is 0, 0, 1, and this is a projection. So naturally it would be, if I use it, it would be K prime T. So as I mentioned, K prime R into K prime T, so it is just simply K prime T. So in this way, 2 epipoles are computed from the camera parameters. So with this, let us see that these are the 2 things we are deriving, but to relate the x and x prime, these corresponding points, what we use, we will use this fundamental matrix relationships between a point and a line. That means the point and the epipolar line on which the corresponding point lie. So from there I can consider this, since x prime lies on this L prime, I can write it as x prime transpose L prime equals 0. There is a point containment relation, and then this L prime is replaced by fx. So you can see now this equation, x prime transpose fx equals 0, they directly relate these 2 point correspondences, and they are the equation here. It's a single equation, because if I look at the dimension, this x prime transpose is 1 cross 3, this fundamental matrix is 3 cross 3, and this X is 3 cross 1. So 1 cross 3, 3 cross 3 and 3 cross 1, they makes it as 1 cross 1. So let me use a better picture. So you have X prime transpose if X equals 0. So to check the number of equations here, what we will find that X prime transpose, here we have a dimension is 1 cross 3 because X prime is of 3 cross 1. If is still 3 cross 3 and X is 3 cross 1. So if I perform the matrix multiplication, the whole thing will be of 1 cross 1, which means I get a single equation. I will get a single equation that should be equal to 0. So I will get a single equation. So each point correspondence will give me a single equation, and this is called the characteristics equation of the stereogeometry. Note that if I take the transpose, I will also get a similar structure. Now with respect to this image, it is X transpose and then the F become F transpose. So X transpose, F transpose and X prime, if I multiply them, that should be equal to 0. So these two equations are equivalent, they will give you the same equation, but the point is that if with reference to this camera, if the F is the fundamental matrix of the stereogeometry, with reference to the other camera, the fundamental matrix of stereogeometry would be F transpose. So that also you should note. So as I mentioned, there is no bias in this case, and you have the similar properties for both the cameras. So finally, let us once again summarize the expressions of fundamental matrix, and also let us see there is a terminology called essential matrix. Now, which is a fundamental matrix for one special case. That special case is that it is simply the two cameras. They are both in the canonical. They are calibrated cameras, which means I will have K equal to identity there, and K prime is also equal to identity. I know the calibration, so I can express the respective image coordinates in terms of canonical image coordinates with reference to that camera. So for that, the fundamental matrix will become essential matrix. So first, let us consider the expression of fundamental matrix, and we have seen that the fundamental matrix can be defined as E prime cross. This is now the cross product operations equivalent. So E prime cross into K prime R K inverse, which is actually the plane induced homography. That means the homography induced by plane at infinity. And then E prime, we have seen it is K prime T. So everything now it is expressed in terms of all the camera parameters. Now when K prime equal to K, that means K equal to identity. So you have this configuration, P is I0, which is the canonical camera configuration, but P prime is a general camera because it is placed in a position and it has orientation. So it can consider a general camera, projective camera representation of M and N. Then naturally for this, as you see that this would be equal to K prime T is M, and here K prime R is also M. This M is K prime R, and K inverse, since K is identity, so this term will not be there in the expression, it is equivalent. So I can write it as M cross M. So this is what the M cross M, this kind of this once again skew symmetric matrix formed by the fourth column. So fourth column P4, M and P4 are same now. So this is the notation we use usually for the stereo when we express the stereogeometry. So, but we could have used P4 here, but we used M, and that actually forms this kind of structure. So this is another form of representation of fundamental matrix. And then for K equal to I and K prime equal to I, then this term reduces to, as you can see, that k prime is I, so k prime, we can make k prime t equal to t. And here also, since k prime and k inverse both are identity, so we can make k prime r k inverse equal to r. So you get this kind of structure, t cross r structure. In fact, if I write the canonical representation of the camera matrices in the stereo geometry, in general I can write in this form for a calibrated camera. And you can see that this r is nothing but the respective m in this representation, and this t is the respective small m representation. So there. Now when we have this configuration, then this f also called, another term is there, it is called essential matrix. So essential matrix is the fundamental matrix of a spatial of the calibrated cameras. So that is the definition of an essential matrix. So I will conclude this lecture by just showing one exercise, just to give you an idea that how these kind of relationships are, how we can exploit the camera parameters or elements of the projection matrices to know about different entities of stereo geometry. So first thing is that if I give you a reference camera, that means left camera in our considerations, in the form of canonical form, that means you have identity matrix for the M part 3 cross 3 submatrix form, and it's a 0 column vector, and it is naturally it is a camera centric coordinate system. You know that all these coordinate axes, world coordinate axes, they are parallel to the image coordinate axis also. And then you consider any arbitrary positions of the any stereo of the second camera, and which has the rotations of the axis, which has the translations. So you have these submatrices. You can see that in this form. Okay. So you have to compute the fundamental matrix. So how do you do it? So as I said that this part could be considered as M 3 cross 3 submatrix, and this one is the 3 cross 1 column vector M. So we should first compute the respective M cross matrix, skew symmetric matrix, and taking from the definitions of skew symmetric matrix, this is what we can get. So this is a x component, y component, z component, and apply the respective mapping to that configurations the way it has been defined. You can derive this matrix, and then you can multiply this with the matrix M, and you can get this M. So this is what is your fundamental matrix. Let us consider another exercise where we have the two camera matrices, and we can see that this is actually given a general configuration. This is not with the canonical configurations, any general camera configurations. Further, how to compute the fundamental matrix. And not only that, what I want that given an image point 1520, that is the position of the reference camera P, compute the epipolar line. So because if you know fundamental matrix, we know that what you need to do, that if this point is expressed in the homogeneous coordinate system, if the fundamental matrix is F, then I will get the corresponding epipolar line. Also, it's two end image points of P prime. So to consider this problem, actually we have discussed already, we have understood also plane induced homography. So we will quickly see that how we can do it. First thing we can see that these are the structures we are using, say M, and instead of small m I am using P4. So the camera centers we can compute. So camera center of the reference camera P. So this is what we will get. This is the camera center in the homogeneous coordinate space. Similarly, the cameras, from there we can compute the right epipole, because the projection of the camera center of the left camera will give you the right epipole, and this is the epipoles. And the other one we will discuss this part, today the time is not much there, but that the line at plane at infinity induced homography, it is already, no, we have discussed that was, if you see, that was KR K inverse, but since now it is M and M prime, so this KR is M prime in this case, so it is K prime or K inverse, this K prime is M inverse, and this K inverse is replaced by M inverse. So that is a plane induced homography. So if I use E cross plane induced homography will give me fundamental matrix. So I have to find out also E because of that. So this is what is your plane induced homography, what you can compute. So as I mentioned, E prime cross H infinity, E prime cross H infinity, that would give me the plane induced fundamental matrix. So E prime cross once again would be derived from here earlier as we did. So these are the components. I can ignore this because it's a projective space. The scale could be ignored, and from there I can derive E prime cross, and then I use H infinity. I multiply this with H infinity, and this is the fundamental matrix what we get. So this is the first part of this problem, that is the fundamental matrix. The second part is that given an image point 1520 of the reference camera, compute the epipolar line and its two end image points. So that means, say this is the image point which is given, say 1520, and the epipolar line can be computed, say this is epipolar line, and so this image points. So these are all, as you understand, these are all possible image points. So in this ray, these are all corresponding points, right? But here with some scene structure, this is the point. So corresponding to this point, there are so many possibilities of corresponding points, and they form that line. And if it is at the infinity, lying at the plane at infinity, so that gives you the vanishing point. That gives you the vanishing point. And for every plane induced image plane, if I apply the transformation h by x, we will get the corresponding image point, corresponding point on the epipolar line. So for the plane vanishing point also, already we know that the plane at infinity vanishing point is m into m prime into m inverse. So if I apply x with m prime m inverse, I will get the vanishing point, and that is the other end point, and epipole is this end point. So this is the consideration. So if I will get the epipolar line by simply multiplying f with the image point. This is epipolar line, and these are the this is the vanishing point along the epipolar line. So this is one extreme, and the other extreme is the epipole itself. So this one is the vanishing point, and epipole we have already computed. So this is the epipole. So with this, let me stop here today, and we will continue this discussion in subsequent lecture. Thank you very much for your patience and listening.